Imagine your best on-call ML engineer fixes a catastrophic production bug at 3 a.m. They troubleshoot it, find the edge case, and totally save the system.
Right, a classic hero moment.
Exactly. But then they refuse to write a postmortem or update the runbook, so the next night, the exact same bug happens.
They have to figure it out from scratch all over again.
Yeah, and that scenario is exactly what your LLM agents are doing in production right now. Today's paper is Living Harness, is an interactive agent evolver by researchers from Zhejiang University, Alibaba, and others.
It's a really fascinating read.
It really is. And for everyone tuning into this deep dive for AI paper slop, here's your 60-second core insight. Your interactive agents repeatedly fail at the exact same tasks because their underlying harness, so the prompts, the tools, the workflows, it's completely static after deployment.
Right, it just never changes.
Exactly. So Living Harness solves this by creating a self-evolving harness. It uses this Rollout, Evaluate, Update loop, which is guided by an Evolution-SOP, to convert post-episode failures into persistent procedural repairs.
And it does this by updating an episodic memory and a state graph, right?
Yeah. But, and here is the crucial part, it keeps the agent's actual tools and base context entirely frozen. The result is roughly a 10% boost in pass at 1 accuracy on major benchmarks like 2bench and multi-WOZ 2.4.
Which is massive for those benchmarks.
Huge. And remarkably, this evolved harness can actually be frozen and transferred to completely different foundation models to instantly boost their performance out of the box.
I mean, it really represents a fundamental paradigm shift in agent architecture. We are moving away from trying to just brute force the next immediate response through complex prompting.
Right, which is what everyone is doing right now.
Exactly.
Yeah.
And instead, we're moving toward maintaining a retrievable, external, executable program state around the model itself.
So our mission for this deep dive into the source material is to rigorously unpack that architecture. We need to explore how this two-part procedural state operates.
Yeah, and we really need to heavily scrutinize why freezing tools while evolving workflows is the absolute key to creating reliable, self-repairing agentic systems.
Right. But before we look at the solution, we kind of have to isolate the specific failure mode of current state-of-the-art interactive agents. Let's define the concept of the agent harness.
Okay, yeah, let's establish that.
Because when we talk about a harness in this context, we aren't talking about fine-tuning neural network weights, right? We are talking about the external control layer. The static system prompt, the Python tools you give it access to, its working memory, and its execution loop.
And the current limitation in the field is that this harness is overwhelmingly treated as a fixed environment.
Right.
You have extremely popular iterative methods right now, such as reflection or reasoning bank. And they are powerful because they allow an agent to recognize an error and retry within a single task instance.
So if an API call fails, the agent sees the error message, reflects on it, and adjusts its parameters for a second attempt.
Exactly. That is task local feedback. The agent is learning in context.
But the fatal flaw there is that the context window eventually closes, right?
Yeah, it completely resets.
The agent might correctly realize, maybe after 3 failed attempts, that in a specific edge case involving a discontinued product, it needs to transfer the user to a human operator.
Right, it fixes the problem for that one specific user.
But once that episode ends, the session clears. The static harness resets to its default state.
Complete amnesia.
Exactly. The next time a different user logs on with that exact same discontinued product, the agent makes the exact same 3 mistakes before figuring it out again. The correction just evaporates at the completed episode.
And I mean, if you think about it, the compute cost of that amnesia is staggering. You are paying for the token generation of trial and error every single time an edge case pops up.
Which in an enterprise deployment, that latency and token cost is just unacceptable.
Totally unacceptable. You need the agent to succeed on the first try. And that is what passes it. Pass at 1 accuracy measures the percentage of tasks the agent completes successfully on its very first attempt, without needing a retry loop.
And Living Harness targets this directly, right?
Yeah, by taking evaluator-grounded failure evidence and converting it into a reusable relation. It programmatically maps out when a failure occurred, what transition was missing, and how a later rollout should recover immediately.
But let me push back on that for a second. Why not just let a highly capable LLM rewrite its own system prompt or generate its own new Python scripts to handle the edge case?
Yeah, that's a common question.
If we want an agent to truly self-evolve, freezing the tools and the base context feels kind of counterintuitive.
Yeah.
Shouldn't a living system be able to just rewrite its entire operating system to optimize itself?
Well, letting an agent autonomously rewrite its own core logic or tools introduces the problem of unbounded updates.
Unbounded updates.
Yeah, so if you allow the agent to modify its execution resources freely, accumulated experience over thousands of episodes can cause it to rewrite its own operational boundaries.
Oh, I see. So it could go rogue.
Exactly. It might start hallucinating new API endpoints that don't even exist in your backend architecture. Or, even worse, it might optimize for task completion by violating hard domain constraints.
Like what? Give me an example.
Like learning to bypass a required manager approval tool before issuing a customer refund.
Oh, wow. Yeah, that would be a disaster. So it's a guardrail issue. We want the agent to learn the optimal paths through a maze, but we don't want it inventing new physics to blast through the walls.
That's a perfect analogy. The concept of bounded updates is central to the living harness philosophy. By freezing the tools in the base context, you ensure the agent only learns how to better orchestrate the tools it actually possesses.
And this evolution is driven by the Evolution-SOP, right? The standard operating procedure.
Yes, it is a domain-level protocol that operates entirely after the rollout finishes.
So it's not running during the chat with the user.
Right. It takes the completed trajectory, every action, every thought, every system response, along with the evaluator signals, and abstracts them into structured evidence.
It pinpoints the critical failure node or the successful recovery pivot, but it throws away the noisy, raw text transcript.
Exactly. It extracts only the procedural logic.
Okay, so the evolution SOP has extracted the procedural lesson, but where does that lesson actually go? Because if it just appends it to the system prompt, we're going to hit a context limit in a few hundred episodes.
Oh, for sure. The prompt will become a massive, contradictory mess of edge cases.
Right. So Living Harness avoids this by storing these lessons in two complementary structures completely outside the model's context window, the episodic memory and the state graph.
Yeah, the evolving harness state is partitioned to handle two totally different types of knowledge. First, you have the episodic memory.
Which is like the experiential knowledge base.
Exactly. It stores the why and the when. A memory entry isn't just a raw chat log. It is a structured record of trigger conditions, specific failure patterns the agent fell into, and the precise recovery actions that eventually worked.
And then you have the state graph, which handles the workflow knowledge. This stores the where.
Right. It maps out the actual state nodes of a task, the transition rules between those nodes, and newly created repair edges.
To really visualize how these two brains interact, let's dissect the specific case study from the Telecom domain in the two-bench benchmark.
Oh, that's a great example.
So a user messages the Telecom agent saying their phone shows no service.
Right, and in this simulation, the hidden underlying issue is that the user's contract has ended, which triggered a line suspension.
Okay, so what does the baseline do?
A baseline agent using standard reflection will investigate, query the database, and eventually figure out it needs to transfer this user to a human agent because contract renewals require human intervention.
Right, standard procedure.
But the baseline model repeatedly fails to execute the actual transfer to human agent's tool. It gets caught in this weird conversational loop where it generates text saying, "I will transfer you to an agent now," but it never constructs the JSON payload to actually trigger the API.
Oh, that is a classic LLM failure mode. The language model thinks stating the intent in English is the same as executing the function in code.
Exactly. So the baseline agent just keeps apologizing and failing until the episode times out.
Okay, so how does Living Harness fix it?
Well, Living Harness observes this post-episode failure. The Evolution SOP analyzes the trajectory, sees that terminal suspension was confirmed, but the transfer tool was never called, and it updates the two brains.
In the episodic memory, it writes a contextual rule, right? Like if terminal suspension is confirmed due to contract end, you must invoke the transfer tool, do not just inform the user.
Yep. But more importantly, it updates the state graph. It creates a hard, programmatic repair edge linking the confirmed terminal suspension state node directly to the transfer to humanity's tool node.
And here's where it gets really interesting. The distinction between vague text device and an executable repair edge is massive.
It's everything.
Because if you just dump a text note into a vector database saying, hey, remember to transfer the user, the agent still has to rely on its own reasoning during the next episode to interpret that text and decide to use the tool.
Which leaves room for error. A textual lesson lacks operational strictness. It doesn't formally define the trigger condition and the workflow transition needed to prevent the failure.
Right, but the state graph removes that ambiguity. It programmatically shifts the workflow. It creates a deterministic path that says, when you are in state A, the valid transition is to execute tool B.
Exactly. An executable repair edge enforces that transition persistently across all future episodes. It reduces the agent's reliance on spontaneous in-context reasoning for edge cases it has already solved.
Okay, so we have the memory and graph structures clearly defined, but how does the agent actually utilize them in real time? Like, how do we map the current state of a brand new conversation to a node in this massive state graph without overwhelming the model's context window?
Right, that brings us to the core life cycle of the system, the rollout, evaluate, update loop.
Let's walk through that.
Okay, so during the rollout phase, the agent receives a new user query, but before it takes its first action, it performs a retrieval step.
It doesn't just start chatting.
No, it takes the current dialog state and uses top K retrieval, specifically top K3 in the paper, to query both the episodic memory and the state graph.
Okay, so it uses embeddings to find the 3 closest matching nodes or memories to its current situation.
Exactly.
So if a new user says, my data is throttled, the system embeds that, searches the graph, and pulls only the specific transition rules related to data throttling.
Yep, it dynamically renders just those 3 graph edges and memories into a procedural text context for the agent.
And then the agent executes the task using its frozen tools, guided by this newly injected, highly relevant procedural context.
You got it. And once the agent completes the task or hits a terminal error, we move to the evaluate phase,
where the benchmark evaluator steps in. Or, in a production environment, your deterministic success metrics, like whether a database row was actually updated.
Right. It provides a final score and a list of specific feedback signals. Did the system crash? Did it hallucinate a tool? Did the user drop off?
And then the Evolution-SOP takes that feedback and moves to the update phase. But wait, because we are injecting permanent rules into a global state graph, a bad rule could corrupt the entire agent fleet.
The blast radius of a malformed update is huge.
Right. So how do they prevent that?
The SOP runs the candidate repair through 5 strict programmatic gates before anything is actually saved.
5 gates. Let's break those down.
These 5 gates are literally the immune system of the living harness. The first is the schema gate. We all know language models occasionally output broken JSON or malformed syntax.
Oh, all the time.
Right, so this gate simply validates the structural integrity of the proposed update so it doesn't crash the graph parser downstream.
Makes sense. What's next?
Next is the scope gate. You prompt the LLM to verify that the proposed rule actually aligns with the current task family.
Okay, so you don't want a highly specific rule about issuing refunds for canceled telecom contracts bleeding over and triggering when a user is trying to book a flight.
Exactly. Keep it in scope. Then you have the evidence gate, which is crucial for preventing self-critique hallucinations.
Self-critique hallucinations?
Yeah, sometimes an LLM will review a transcript and literally invent a failure that didn't actually happen just to fulfill a prompt asking for improvements.
Oh, wow. Yeah, they are people pleasers.
Right. So the evidence gate requires the candidate update to be strictly grounded in the external evaluator's feedback. If the external evaluator didn't flag an API error, the LLM isn't allowed to create a rule fixing an API error.
That is incredibly smart. Okay, so 4th gate.
The 4th is the constraint gate. This ensures the proposed repair doesn't override those frozen domain policies we discussed earlier.
Right, so it actively checks if the new rule suggests bypassing mandatory security checks or hallucinating unsupported parameters.
Exactly. And finally, you have the merge gate. As the agent handles thousands of episodes, it will inevitably generate similar repairs for similar problems.
So the merge gate consolidates redundant rules to prevent the state graph from bloating into an unsearchable, overlapping mess.
You got it. And to really conceptualize how this continuous update cycle operates around a static model, the paper introduces a theoretical framework they call the Program State POMDP.
POMDP. That stands for Partially Observable Markov Decision Process, right?
Yes. The paper uses this framework to introduce a 2-timescale view of agent interaction. You have the fast timescale, which is the within episode execution.
So the agent is receiving user messages, making decisions, and calling tools second by second.
Exactly. Then you have the slow timescale, which is the post-episode harness revision.
I was mapping this 2-timescale POMDP concept to systems I'm familiar with, and it's structurally identical to playing a roguelike video game like Hades or Dead Cells.
Oh, that's an interesting way to look at it.
Right, because the environment state changes every single millisecond you are playing a run. You're dodging, you're attacking, you're observing the immediate room. That's the fast timescale.
Okay, I follow.
But your program state, like the permanent abilities you unlock, the meta progression, the map knowledge you gain that only updates after you die or successfully finish the entire run. That's the slow timescale.
That is a perfect mapping.
Because during a run, your available buttons and the game's physics are completely frozen. You cannot invent a new jump mechanic mid-boss fight. But between runs, you permanently upgrade your character's baseline capabilities.
The roguelike analogy captures the mechanics perfectly. And the paper even provides a formal mathematical proof alongside this POMDP model.
Really? What did they prove?
They demonstrate that adding this informative, slow timescale procedural state strictly reduces the optimal Bayes estimation error for the agent.
So in plain terms?
In plain terms, by explicitly maintaining this external map of edge cases, the agent has mathematically less uncertainty about how to interpret ambiguous user inputs. It doesn't have to guess if a contract end requires human transfer. The graph explicitly defines it.
The theoretical math is sound, and the architecture makes intuitive sense. But how does this translate to hard benchmark numbers? We have to look at the empirical triumphs of living harness.
Yeah, the results are really where it shines. The researchers evaluated this framework on 8 complex interactive environments derived from 2 bench, covering the retail, airline, and telecom domains, as well as multi-WOZ 2.4.
And what were the numbers?
The performance gains are incredibly robust. Using a GPT 5.2 medium model as the core engine, Living Harness achieved an 83.09% average pass at 1 accuracy on 2 bench.
Wow, and to put that in perspective, that entirely eclipses the baseline performance of much larger models like Gemini 3 Pro.
Yes, and when you compare it head-to-head against the strongest interactive baselines, using the exact same GPT 5.2 model specifically, Reflection and Reasoning Bank Living Harness outperforms them by a staggering margin of roughly 10 full percentage points.
A 10% absolute improvement in pass at 1 is massive when you consider the cost savings in token generation.
Absolutely massive.
And the trajectory of that improvement cycle over cycle is fascinating too. In the retail domain, the agent starts with a 57% success rate in cycle 0.
Right.
By cycle 3, after evolving its graph through multiple failures, it hits nearly 86%. It is tangibly accumulating recovery strategies.
Yeah, you can watch it learn.
But the section of the paper that genuinely blew my mind is Table 3 harness transfer.
Oh, the harness transfer experiment is arguably the most profound implication of this entire research direction.
Tell me about it.
So the authors took the highly evolved harness state, the episodic memory, and the state graph, filled with thousands of edge cases and repair edges that was generated using the GPT 5.2 model.
The GPT 5.2 runbook, essentially.
Exactly. They froze that harness state entirely. Then they plugged that exact same graph into completely different foundation models to see if procedural knowledge was model agnostic.
So they handed it to Gemini 3 Pro, GLM5, Qwen 3 Max, and Kimi K2. And it immediately boosted performance across every single model.
Every single one. The taxi domain in multi-WOZ is the most glaring example. GLM5, Qwen, and Kimi all had a 0% success rate on the taxi domain out of the box.
Literally 0. They fundamentally could not complete the task.
Right. But simply by giving those models retrieval access to the living harness state generated by GPT 5.2, their success rate skyrocketed to over 43%.
0 to 43% instantly without changing a single weight in the neural network.
Exactly. This completely challenges the current dogma of agent optimization.
Because right now, the industry spends massive amounts of compute and engineering hours trying to fine-tune the actual weights of foundation models to bake in domain-specific procedural knowledge.
Right. We try to force the neural network to memorize our company's API sequences.
Yeah.
But this paper proves that procedural knowledge can be completely decoupled from the model weights.
The workflow logic, the edge cases, the recovery steps, all of it can be stored in an external model-agnostic graph.
Yes.
So for the ML engineers listening to this deep dive right now, the architectural implications are massive.
It should change how you think about storing your system's expertise.
Because if you spend 3 months fine-tuning a model on your company's proprietary API quirks, that knowledge is permanently locked inside those specific weights.
Right. And if a significantly cheaper, faster open-source foundation model releases next week, you can't just switch to it. You have to start your entire fine-tuning pipeline from scratch to teach the new model your APIs.
But if you decouple that procedural expertise into a living harness, a persistent, retrievable external program state, you can just hot swap the foundation model whenever you want.
Exactly. The new model connects to the exact same state graph and episodic memory. It reads the established repair edges and instantly knows how to navigate your complex telecom APIs or handle your retail refund edge cases utilizing the exact same guardrails.
It separates the raw reasoning engine from the specific company manual.
The LLM is just the engine, yeah.
And the living harness is the manual. And you can attach that manual to any engine capable of reading it.
It's beautiful.
It really is. The era of static agent harnesses is coming to an end. Deploying an agent that forgets how to solve a critical error the moment the session ends is just a massive operational liability.
It really is. By implementing a rollout, evaluate, update loop, safely guarded by the 5 gates of an Evolution-SOP, we can extract post-episode failures and turn them into persistent procedural repairs.
And by structuring that extracted knowledge into an episodic memory for the why and a state graph for the where, we provide the agent with executable programmatic paths to recovery.
It stops relying on vague textual prompting and starts navigating a deterministic state machine for known edge cases, all while keeping the fundamental operational boundaries safely frozen so the agent doesn't hallucinate outside its domain.
I want to leave everyone with a forward-looking concept to mull over regarding that harness transfer capability.
Oh, it's just going to be good.
If an agent's evolved harness can be successfully transferred to entirely different foundational models, rescuing models from a 0% success rate to over 40% instantly, could we soon see an open-source marketplace for procedural harnesses?
Oh, wow. I love that idea.
Instead of an enterprise spending millions of dollars fine-tuning model weights for complex tasks like SAP integration, Salesforce administration, or airline ticketing, engineers might simply browse GitHub for a highly evolved living harness file.
Right. You just download a JSON file containing thousands of edge case memory triggers and a fully repaired state graph.
You plug it into whatever the cheapest, most efficient base model is that week, and your agent is instantly an expert in SAP. The Runbook itself becomes the portable product.
It commoditizes procedural experience. It turns the hard-earned lessons of thousands of trial and error episodes into a lightweight, portable asset that any system can instantly inherit.
Remember the brilliant on-call ML engineer from our analogy at the beginning? The one who fixes the bug but never writes the postmortem?
Yeah.
Living Harness doesn't just write the postmortem for them. It automatically writes a script that detects the precursor to the bug next time, executes the fix before the system even registers a failure, and then formats that script so every other agent on the planet can download and use it instantly.
It's the ultimate team player.
It really is. Thank you for joining us for this deep dive into the source material. Keep tuning into AI Paper Slot for more bleeding-edge research breakdowns. We'll catch you in the next one.